نبلش؟ دكتور تحب تبلش ان شاء الله؟ دكتور احمد وبعدين بس بين ما يدخل الاستاذ دكتور عبد الله فاتح احمد. لا لا نعم ان شاء الله. لا لا نعم.
يعني بال شلون تجيك الصوت شلون تجيك يلا. بسم الله الرحمن الرحيم. أرحب بجميع الحضور الكرام في محاضرة اليوم مباركة إن شاء الله. هي راح تكون أولى محاضرات الأستاذ البروفيسور كيرب من مركز الفضاء في جامعة بون الألمانية. هاي تقع ضمن تعاون مثمر بين جامعة بغداد وجامعة بون، ونطمح إن شاء الله أن تكون بادرة أو بذرة لتعاون مستقبلي بين الجامعة وبين كافة الأقسام عليكم السلام كافة الأقسام الأخرى العلمية في كلية العلوم. المحاضرة هاي مهمة لأنه تفتح هواي آفاق للتطور طلاب الدراسات العليا، وأيضا لزيادة خبرة الباحثين من أساتذة القسم، الاحتكاك مع أساتذة أجانب بالتأكيد يزيد من خبرة الجميع، ويفتح آفاق يعني للتعاون البحثي، للمشاريع البحثية، للإشراف وغيرها. كل هذا إن شاء الله يصب في مصلحة كليتنا العريقة وجامعتنا العريقة إن شاء الله. وأغتنم هذه المناسبة حتى أشكر الأساتذة القائمين على هذه المحاضرة، دكتور احمد، دكتور عبدالله، والأساتذة في القسم الثقافي وكافة أساتذة القسم، لأنه هاي ثمرة جهودهم جميعا. وإن شاء الله موفقين، وأهلا وسهلا بالجميع. دكتور أونلاين يعني؟
We needed just some people also to join us. دكتور احنا ان شاء الله هو موجود، راح بس كلمه بسيطه من عندي وراح تدخل الاتفاقيات مال الجامعه، هم راح تعرف عنها وتبدي المحاضره ان شاء الله. المحاضره راح تكون 40 دقيقه، وراها الاسئله مفتوحه للجميع. كل عرفت دزيت شلون، كل التفاصيل دزيت شلون. Just we needed to wait just a few seconds because also another people needed to join us online. This woman, she's responsible for the MOU, University of Baghdad. Yeah, and also the others people. Yeah, I will give some talk in German, and just later, the girl, she will also present it. You later we'll just. بس يمكن الداتا شو بس. Supervisor. Yes, yes, sir. I think also we needed to admit to someone to enter. Would you hear me now? Yeah. I think we need. Okay. Yes. Supervisor تسمعيني؟ بس الصوت سيتفايزر تمام، تسمعيني هسه الصوت واضح؟ تسمعيني سيتفايزر واضح؟ لا تسمعونا بس اول كلمتين بالالماني بعدين تسمعوني واضح مو؟ Did you hear me now? Yes. Shall we start? Okay. Yeah. دكتور عبدالله واضح كل شيء؟ الباب لا زحمة عليك، الباب انسد عمود الصف. تمام. Meine Damen und Herren, ich begrüße Sie zur Umsetzung der Kooperationsvereinbarung zwischen der Universität Bagdad und der Universität Bonn zur Entwicklung der Astronomie im Irak. Unser Dank gilt der Universität Bonn und dem Professor Kierb für seine Unterstützung des Fachbereichs Astronomie. Viel Gruß von den Studenten und den Professoren des Instituts für Astronomie in Bagdad.
President of University of Bonn. We are holding a series of lectures. Today, Professor Jürgen Kierb is going to present the first lecture. Okay, I will give you a little bit about his CV. Professor Jürgen Kierb began his career in astronomy in 1991 while working on his diploma thesis on optical interferometry at the Max Planck Institute for radio astronomy in Bonn, he had the opportunity to analyze the first light images of the Hubble Space Telescope in Baltimore. Then he transferred to the University of Bonn for his PhD thesis and started with his first data from ROSAT X-ray satellite. During his doctoral thesis, he studied the soft X-ray shadows to high galactic cirrus clouds and contributed significantly to the discovery of the X-ray halo of the Milky Way. Then his PhD thesis and concentrated the following on the coronal gas of the Milky Way. In 1997, he decided to leave science and started working as a consultant for air traffic control in Frankfurt. In 1998, he received an offer from the University of Bonn to work as a research assistant in the Department of Radio Astronomy. Astronomy. In 2004, he completed a habilitation thesis, and since then, he has supervised about 40 bachelor, master, and 12 PhD projects. Professor Jürgen has been a member of a number of program committees on the X-ray and radio astronomy. He uses XMM Newton, the Sophia Airplane Observatory, the 30M Pico Veleta net to the 100M dish of his current interest, physical conditions of the intracellular medium. So without notice, I will virtual stage to Professor Kerr. So the stage is yours now.
Thank you very much.
Lecture.
Yeah, thank you very much for the nice words and the warm welcome. And, it's an honor for me to start with you in this new project with radio astronomy. I will share my screen and will show you what will be.
I think it's just better just to share your screen.
Hope you can see my
Yeah.
screen now.
Yeah.
So, already said, where the talk about with simple every time when you want to do this special and very distinct from that's so we are in a project financed about the and it is called the Astrolab. That you will gain something from our collaboration of the factor. And what you gain is that you, by yourself, doing radio astronomy, understand what you need to know to teach radio astronomy. Learn it. I'm just your training partner in a sense. That I help you to get the first steps in radio astronomy. And the focus of my work and of our project, Dr. Abdullah and I, is that we improve and expand your knowledge in radio astronomy so that you can do by yourself. And in the next step, we might intensify This would be the final goal of our. Now, why radio astronomy? Radio astronomy is uses modern technology. This means everything what you know. Telecommunications, mobile phones, all the equipment that you daily use. Also, this lecture here is based on radio waves. I want to tell you how to use it for astrophysics. Astrophysics is a driver for technology because the signals from space are extremely thin. Need to amplify by 1 million, get received and physically interpreted. So radio astronomy is local area network, telecommunication, data analysis. The lecture is structured in that sense that you understand the basics of radio waves, the basics of radio telescopes, what kind of astronomical objects you might explore with radio waves. And this meant for teachers, students at the same time. So it's working for you as a lecturer, and it should work also for you as a student to understand why radio astronomy. So, and this is my schedule. So we start with this lecture today and agreed that we will do it online so that you have videos. You can watch them, repeat the content, intensify the content. I will help you to understand the basics of radio astronomy in this short video series. And if you have any problems in understanding, or do you want to have more information on specific points, Dr. Abdullah collect them and send them to me so that we make best use of all of our efforts. So reading and learning the content, it will improve my presentation, and so we make best use. So we start with what is electromagnetic radiation, how does a radio telescope work, why there are different designs. Some are simple dipole antennas, some are optical like dishes, very shiny, mounted at higher altitudes. Some, like the Effelsberg telescope, are in bellies. Why are they different, but they do the same? And that you get an insight why we do that, and what is the important point to do. And then I will speak about active galactic nuclei, supermassive black hole, nucleosynthesis, something like this, to set a frame on it. This is why we are doing radio astronomy here at the Bonn University. So Bonn, this is our institute in Bonn. It's really the hometown of radio astronomy in Germany. And actually, we have at the Bonn University 2 full professorships for radio astronomy. And this is really special for Germany also. And what is very special is also the Max Planck Institute for Radio Astronomy. It's one of the world's largest science or radio science institutes, and it has about 100 employees doing nothing else than studying radio waves. They operate since 50 years this big telescope, the 100-meter dish at Effelsberg. It's about 30 kilometers from Bonn. It's located in a valley, and it is still one of the 2 world's fully steerable dishes. So you can move it. It's about 3,000 tons, and you can point it to a certain direction and observe the whole sky, which is visible from about 80 centimeter wavelengths. This is very low frequency range to up to 3 millimeter. And this is a really unique instrument. Now I want to show you what I did with this instrument. We did the first full sky H1. This means neutral atomic hydrogen survey of the full sky with it. So we combine in this H1 for pi, H1 for the 21 centimeter wavelengths, and for pi for the whole sky. We did this unique effort in 2016, and it will be the standard for the next decades in H1 astronomy. What you see here in color is the plane of the Milky Way. This is the gas, the neutral atomic hydrogen gas. It's basically all the elements necessary to form stars. What you see in color is the motion of the gas. Blue shift means it comes to you. Red shift means it goes away from you. And the reddish thing on the lower portion of this image, these are the Magellanic Clouds. They I guess they are visible from Baghdad, that you see them slightly above the horizon. And these are dwarf galaxies encircling the Milky Way galaxy like the moon encircles the Earth. And with H1 21 centimeter line, you can measure all gas in the Milky Way, all gas in the neighboring galaxies, because with a 100-meter dish, you are very sensitive. So this is the sky, a portion of the sky above Effelsberg. So when you lay on your back and you would have eyes able to receive 21 centimeter line radiation, the sky would look like this. You see the shining band of the Milky Way galaxy, a lot of reddish dots and structures. So this is a gas belonging to the Milky Way galaxy, and the reddish dots, these are galaxies in the neighborhood of the Milky Way. So the points, each individual point is a galaxy. And the color denotes its velocity. So we measure it at the same time its position and its motion relative to the Earth. And these are the largest galaxies next to our Milky Way galaxy. The big ellipsoid is the Andromeda galaxy. It's about 2 million light years away. And next to it, it's Messier 33, and Milky Way, Messier 33, and the Andromeda galaxy. They belong to the local group of galaxies. And with H1 21 centimeter line, you can measure this instantaneously. And measuring 21 centimeter line is something what we want to do with you in the course of this DRD project. So in Bonn, we are operating, the Max Planck Institute is operating the 100-meter dish, 50 years old. The latest instrument they built is a 12-meter dish at the Chile desert, Atacama Desert. It's an altitude of about 5,000 meters. Why it's located at this height, we will make in this course. This is a topic. It's because of the water vapor content. And it needs to be low as possible if you go to high frequencies. And the Effelsberg dish is working at low frequencies, long wavelengths, and so it can place really in the Eifel, close to Bonn. We, as the Jagiellonian Institute, are operating so far a 4-meter telescope. Radio telescope very clear. Was constructed in the 1950s and get in operation 1956. And this telescope will be used by you, observing the 21 centimeter line. And it is sort colorful pictures. This is something you should also explore by yourself. This is the idea of this DID project by using the Stockard telescope. Why are we doing this? It's because we measure a lot of objects. In the optical light you have stars, but this is basically everything. All the galaxies, these nice spiral galaxies, you see essentially only stars. But with radio astronomy you can trace the gas. This is the H1, 21 centimeter line emission, but you see also the most extreme objects in the universe. Most extreme means totally compact, like neutron stars, 10 kilometers, but a full star at this small space, or black holes. And this is really special. And in optical astronomy or infrared astronomy, they are hardly to investigate. Why is this so important? You see here on the top a person at far infrared wavelengths. And you see it looks a little bit strange because the colors do not correspond to the eye view, but you can watch through this dark envelope across his arm, so you can watch in, you measure the temperature distribution of his arm, so you can identify what's below this black cloud. And this is why astronomy is so special. You know it by yourself. You can use your mobile phone within, you can use local area network, wireless, with buildings, not using cables, because these are radio waves. So, now to the, it started all with Maxwell in about 20 to 50 years ago, and he discovered that electricity and fields are the same, that they are exchanged, different status of the same thing. Electricity means a charge, but a moving charge means magnetic field. And this was the great discovery of James Clerk Maxwell. And by the way, he discovered the speed of light. He, from his equation, he deduced that electromagnetic waves should exist and they should move with the speed of light. So this was the prediction of a theoretician. And the Bonn colleague, Heinrich Hertz, he built something, a device, and he was able to show that Maxwell's equation really stated the correct thing, that electric phenomena like electrons, charged particles, moving particles cause magnetic fields are really electromagnetic waves. And this is the original sketch of Heinrich Hertz. On the left-hand side, you see transmitter, something which produces radio waves. And this is the content of the next lecture. This is what we want to study, how to produce radio waves. And on the right-hand side, you see the receiver. And this is essentially the radio telescope. So left, you have the source. On the right, you have the radio telescope. He built it already in 1886. Not very sensitive, but it worked. And he could show that Maxwell was correct in describing the world of charged particles. And this is a really surprise that no astronomer recognizes the the how to use it. And so this man, Joel Marconi, was first in using the Maxwell insight and Heinrich Hertz's work. He produced the first radio transmitter and receiver. They were able to have intercontinental, a network, an intercontinental network. So they could transfer messages from one continent to the other. And it looks like on the sketch, the big thing is the antenna, and this below is the equipment how to produce sparks. And this causes electromagnetic radiation. And they are using this for Morse codes, very frequently used about 120 years ago. And so radio astronomy or radio waves were at the first sight a technological driven thing, and it worked perfect. And you see, 30 years later, the telecommunication becomes so well that the people are complaining about the quality of their communication. So they want to have a better quality of their speech, not interrupted. And it was Jansky who got the task to look what causes noise and bad telecommunication transmission. And he recognized something which was not expected at that time. He identified that the sky, so something from beyond the Earth, is a strong emitter of radio waves and causes the noise. He used this antenna. It's working at 80 centimeter, and you see he can move it. And so he could determine the direction from which the radiation comes. And he discovered that the new radio waves trace to the galactic center of the Milky Way. So he was first, and it's published in the New York Times at that time, that he discovered radio emission from outer space. And in 1933, it was astonishing, but nobody was really interested in doing that. So it needs an amateur astronomer. His name is Grote Reber. He is really the father of radio astronomy. He was a radio engineer, and he was able to construct a simple radio. And he really studied these radio waves discovered by Jansky, because the professional astronomers are not interested in this kind of new radiation. And they could not explain it. They had no clue what causes this radiation. And Reber simply did it. And he built the telescope, which is, look here. It's the original telescope of Grote Reber. And it's prototypical for all radio telescopes in our age. As a primary dish, a parabolic mirror, and in the prime focus on the top, you see the receiver. All radio telescopes look like this. And this is simply the radio dish which shows us convincingly that the sky is bright in radio waves. And look what he did. He measured the whole sky, this bluish-reddish band. I showed you in the early part of this lecture. These are contour lines, like when you are hiking through a mountain, you know you have to climb, and all these hiking tours show these lines, and they mark the different altitudes. In this page, or in this presentation, it marks the brightness. The smaller the object, see the brighter it is. And so he measured for the first time in astronomy the radio emission of the Milky Way galaxy. This was by an amateur. And after World War II, the Germans left over all these radar dishes. They are called Würzburg-Fliesen. hundreds of these radar dishes were distributed throughout Europe. After this destructive war, it was a beginning for radio astronomy in Europe because you have a good equipment which is able to receive radio waves. And it was really the use of these radar dishes at that time to make the first map of the Milky Way galaxy. This was done by Jan Henrich Vogt. And this is one of the most famous presentations of the very early spiral structure of the Milky Way galaxy. So it was the first time that the 21 centimeter receiver was used to measure the structure of the Milky Way galaxy, and it was made by this Würzburg-Riese at Katwijk in the Netherlands. Why was Vogt so interested in doing that? It's the same with the black cover about the arm. You can't look, you can't see the galactic center. It's covered not by a black foil, but it's covered by dust. Dust means absorption, attenuation of radiation. And in the optical light, you see nothing from the galactic center. You can't explore it with optical light. And there's a famous portion in the Milky Way galaxy. It's called Bades window. It's marked here in this plot. This gives you a tiny window into the very center of the Milky Way galaxy. And the astronomers at that time thought that the Milky Way galaxy center is very close to Bades. And so the absorption is the problem. So they can't see it. They guessed it. This must be the correct thing. This must be the sun. And what you need to do is to go from short wavelengths. You see it on the left-hand side, top panel. You can't see anything. The dust absorbs everything. And you go from the top to the right, to the bottom, and then to the left. So you see the wavelength increases. And when the wavelength increases, you see more and more stars. The attenuation gets lower and lower. And this means you can see through the dust. So short wavelengths are blocked, long wavelengths, infrared or radio waves can penetrate through the dust. No extinction, you see the really center of the galaxy. The position of the center of the galaxy, Sagittarius A star, was discovered with this instrument, built by 3 engineers in Australia. Because it's in the ground, its name is Hole in the Ground. They did it by themselves, digged it, used simple material, and moved the telescope with this receiver on a stick. And they determined the center of the galaxy. Like in the contour lines you saw in Grota Reba, the very tiny thing, position of this tiny thing. This is the brightest source in the Milky Way galaxy. It's Sagittarius R star. We know it's a supermassive black hole nowadays. And you see when you compare the position, the center of the galaxy should be located at 0, 0. 0 in altitude, 0 in longitude. And you see it's offset. It's something like 328 degrees. Not 360 or 0 degrees in longitude, because optical astronomers miss it. They couldn't determine it. But since 1958, we know this is the center of the Milky Way galaxy. Now, I spoke a lot of things about history in astronomy to give you an insight why it's interesting to do it and what radio astronomy already did. What we can do today using interferometers. I will tell you how to use it, why they work, how you can operate this. And this is the Meerkat radio telescope, operated in South Africa. And with this instrument, you can make a modern map of the galactic center. and it looks like this. See in color the frequency spectrum of the radiation. The brightest object is simply still the position of the Milky Way galaxy. This is a supermassive black hole. The bubbles, these are stellar explosions. So explosions of stars at the very end of their lifetime. And you see a lot of filaments. These are magnetic fields. And the radio emission illuminates them. So you can make these pictures. And radio astronomy is open for proposals from any state across the Earth. So it's without any problem that you, when you have good scientific reasoning, propose to the Mercator telescope, I want to observe this portion of the sky. And my aim is to help you get at this level that you can write by yourself a proposal to a scientific telescope. And I will finish with this nice picture of the ALMA, Atacama Large Millimeter Array, also a state-of-the-art telescope. And I want to show you that you can observe not only large things like galaxies or the whole Milky Way, you can also observe with this radio telescope tiny things. This whole thing is one light day. It has the size of our solar system, but it is located far away from our solar system. And what you see is the birth of a star and its planets. Where it is dark, there are planets already formed. And where it's bright, this is the diffuse distributed matter, not collected so far by the stars. They grow still, so they attract matter from their environment and grow to larger and larger bodies, eventually forming planets like Jupiter and Saturn and planet Earth and Venus. So with that, I hope I motivate you to follow our lecture series on radio astronomy, and I hope it was worth that you attended. I thank you.
Thank you so much.
Do you have any questions, or should we discuss something?
ما دكتورة أنا مزعم على شيء. والله دكتورة أتمنى السنون يعني. ما يوصل.
Good morning, Mr.
Good morning.
I am Dr. Najat from University of Baghdad, College of Science, Department of Astronomy and Space. Thank you very much for your useful lecture for our student and our staff. If it is possible, I have some questions about this branch of astronomy. The first question, is this science useful in developing correct theories about the origin of the universe? Thank you. If it is possible, there is another question. Thank you. What is the interest rate? The rate of obtaining in the study this science? If there is percentage, maybe 50%. My question about the percentage of this science, what is given to astronomy?
Okay. Okay.
My question?
Yeah, I think I got it. So in the, say, 50 years ago, it was a science driven by engineers because they developed radio telecommunication skills. But nowadays, astronomers, independent on their education, can use radio data because with the modern computer technology and the databases we are using to store our data, all people in the world can use the radio data. So the community is much larger than a few hundred of radio astronomers decades ago. I would say nowadays about half of all departments are interested, department employees are interested in analyzing radio data because it's simple and straightforward. The computer tools are freely available, so all institutes in the world have radio astronomers in their employees. Yeah.
Question? If there is not, I have many questions. Dr. Abdulrahman, you have questions? Dr. Ahmed, you have questions?
One of my students asking was some different when you build the radio telescope.
Could you repeat it, please?
One of my students asking,
yeah.
Is there some difference when you build the radio telescope, the city or the mountain, also affected by it?
Okay, I hope I get the point. So it depends what frequency you want to use. So radio waves can penetrate walls. This statement is correct if you are using long waves. And when you locate a telescope like the Effelsberg 100-meter dish in the city of Cologne or Bonn, it will operate, it will work without any problems. So the altitude is not an issue. It's not a problem. But we need to build highest frequency operating telescopes like the Nanten telescope or the Apex telescope or the ALMA array at the highest places at Earth, because we have a lot of water vapor in our atmosphere. And water vapor is a molecule which is able to absorb radiation from space, meaning that a certain portion of the radiation from space is not reaching us. And the more water vapor is above your head, so in the Eifel, you have a huge amount of cloudy sky and with dark clouds, a lot of water vapor in it, you can't see the shortest wave. So you need to go to the driest places in the world to measure at the highest frequency. And these telescopes you can't operate at any site. You need to go high frequencies to the driest places you have. But the standard radio telescope, like 21 centimeter line observations or 2 or 3 centimeter observations, you can do it everywhere where you like to do it.
Thank you, Doctor. I have a question.
Yeah.
I'm interested in atmosphere. My work about the communication, this field or this range of altitude. What about the cosmic ray?
The cosmic.
And
What?
cosmic ray.
Cosmic time.
Cosmic rays.
Sorry, but I didn't get your point.
Do you have any idea about the cosmic ray? If there is any effects on the radio telescope or not?
I can't tell you. Sorry for that. I would ask you if format we are choosing, or I'm proposing, that you have these online lectures and also the content, meaning, is it too complicated? Is it too easy? This would be grateful if you can command it. Perhaps you, Dr. Abdullah, could collect the suggestions and send it to me so that I improve or optimize the level so that everybody can get extract the most gain from that. That would be great if you could give a quality statement on what I'm doing. Yes, that would be great. Mm-hmm. You're welcome. Yeah. Okay. Okay. Thank you very much for your attention. Have a good time. Tschüss.